So hello again. This is, I guess you could say, the second part of the quantum computer capability being mapped onto classical computers. So Quantumistic Volume 2. So the presentation that I posted earlier today called Quantumistic Computing, this is kind of the follow-up to that, a little more deep dive into the actual calculations. I mapped on the different aspects of quantum computing, things like superposition and entanglement, and how you might do those using either modified classical computers or using field programmable gate arrays. And also pointed out all of the downsides to current quantum computing technology. The old saying is, if it sort of looks like a duck, walks like a duck, quacks like a duck, if I can get the useful aspects of quantum computing mapped onto classical computing as computers or add-ons to computers through like field programmable gate arrays, then that's probably sufficient. If you can make it do the same role, if you can make it perform the same function, it doesn't matter whether it's, quantum scale or not, it's performing the function. So at least tonight's the last quantum computing presentation, at least for a while, unless something comes up or somebody requests something. Bear through this one. There's actually a couple fewer slides this time than last time. So if you ever look at any algorithms associated with quantum computing, you'll find that classical computers are considered NP complete, as in when you give it an algorithm, it runs the algorithm until it finds a solution. Whereas quantum computers get you kind of an approximation. It gets you in the general direction, and depending upon how many runs of the quantum algorithm, you'll get closer and closer to something that's sufficiently optimal. And then you can stop there. Whereas with a classical computer, it'll get you all the way to the end. So maybe for classical computers to be just as good as quantum computers, instead of doing all possible of something, maybe we need to pre-filter what it processes so it doesn't have to do all of something, because that's the usual ding that the quantum computing world will poke against the classical computing is, if I want to calculate, let's say, the prime numbers from 1 to 1,000,000, I have to look at every possible number before I can factor it. We already know the prime numbers up to that point. So if we're looking for prime factors, maybe we can just work with the smaller subset of just the prime numbers and not all the non-prime numbers. The second thing is, when we're executing instructions on a classical computer, nobody gives it a second thought, but if you want to do something like a divide, you're doing a full-blown integer divide when whatever value you're running through it may not need the full-blown capability of a divide instruction. So maybe we can narrow that down to make the classical computer even faster. And the other thing that I guess most people in the promotion of quantum computers is they talk about a run or an optimization. They don't tell you how many they have to run. I saw that one of the quantum supremacy algorithms said they had to run over 10,000 runs, and it took them a while to do that. But when they tried to compare that against a classical computer, they only compared one run. That's not telling the whole story. So I was looking at how the current capabilities of classical computers could be put to use to implement the functioning of quantum computers. And for those that are not aware of it, there are instructions on AMD and Intel and even ARM processors these days that are called single instruction multiple data. That's where the software says, hey, computer, execute this instruction for me. And here's an entire bank of data values, or here's a matrix, and I want you to do a dot product on this n by m matrix. And it's a single instruction that runs for a while, but that's a single instruction, and it's optimized to do a lot of things in parallel. Well, if the folks that promote quantum computers aren't aware of SIMD instructions, then they're not giving the classical computers their fair due. The second thing is that if you wanted to implement something like one of those Toffoli gates, where you could have a single gate definition that would do any number of functions based upon what you told it to do, you can implement that stuff in field programmable gate arrays and have a load of them, lots of rows, lots of columns, and then you run your data through it just like as if you were flowing data through a quantum computer. And the individual stages will execute, let's just say, roughly 1,000 times faster than on a quantum computer. The other thing is when you talk about qubits on a quantum computer, it may come in as a digital value, but then it takes on this non-deterministic value. And then when it comes out the other side, after it's run all its operations, then it gets converted back to a deterministic 0 or 1. While a classical computer can do that broadside as arrays using these SIMD instructions or FPGAs, and they can do it on 4 bits, 8 bits, 16 bits, which gives you a lot faster way of doing it over a very large set of numbers. You don't have to do 1 bit at a time. So I had to look up the details on these SIMD instructions, and there's whole families of them. The most current one is called SIMD AVX512, and if you can guess it, it's because the encryption algorithms needed 512 bits of processing, not just 256 bits. So 512 bits. But in general, where they came from was processing things like video streams or digital signal processing. So they started out with, I can do, 8 registers at a time. I can do 8 items at a time with 1 instruction. And they started out with like 64-bit and 32-bit. And then they moved it up to 128-bit. And this latest update is it's still only 8 registers, but they're now 512-bit registers. So you can see how they've been increasing the fidelity or the number of bits for the parallel executing instructions. But they have an upper limit. But to give you an example of how some of these smaller, narrower registers are used, when you're doing 3D animation and you have one thing overlapping another thing, and you want to expose only the things that are in front of or behind this layering, then these SIMD instructions will go process entire wax full of widgets as they overlap. And in the case of video, when you see, I went into Zoom and I selected, I want hardware accelerated video because I want to be able to do like artificial green screen kinds of things. And that's what they're doing. Each line of video gets run through these very fast parallel executing instructions to make the video background work. Because these SIMD instructions might run for a while, not like seconds, maybe good portions of a millisecond, they have to be resumable, as in you don't want to hold up process switching in the computer's operating system if one of these instructions wants to go run for 100 milliseconds. You want to context switch faster than that between different processes running on the computer. So what they can do is they can interrupt one of these instructions, save all the registers, and then when that process gets to execute again, they can resume and reload those registers. But that takes a lot of time. So they've got a per process flag that says, does this process use any of these SSE instructions? And if so, on a context switch, save them out, and on a resume, restore them back. But that's time. So to save the time, they give you an option that says, nope, not using any of that. Oh, my context switching will be faster. So as I was saying, where these SIMD instructions are used is in video processing for things like the virtual backgrounds. You're not likely to see these specific instructions showing up in higher level languages because their use is so infrequent. Right now they're executing probably thousands of times a second to get this video background of me doing this, where you can actually see things. That's not at I won't find a C statement in the C programming language that says go off and do a dot product using one instruction. And it's not likely that the developers would code specific functions in the higher level languages for these instructions because the instruction most of the time doesn't run for that long a period of time. If I'm going to do 8 registers of 8 bits, it might only be a good portion of a microsecond. So I wouldn't want to write an entire subroutine that just did that one instruction, because the subroutine call and return processing would take longer than the instruction is going to run. More likely what you see is something like Zoom's video refresh, how many 60 times a second that's going to run. And somewhere in there, they've implemented by a direct machine language call, assembly language call, the execution of one of these instructions. There's no overhead to get it set up. There's no overhead when it's done. It operates directly on the data. That's kind of limiting as to trying to use this for a larger purpose. But where they are used, they're very useful because they take a lot of processing overhead out. It would otherwise be a lot of iterative processing. They do it in parallel. And I thought, well, would it be possible to at least make the digital to quantum, superposition, entanglement, and detangling functions, use SIMD instructions for those, and on a single qubit basis, probably. But if I wanted to do something wider, like 18 bits wide, the SIMD instructions would run out of steam, so to speak. So they're probably not the best approach for doing that. Why don't we just make some new instructions? Well, as I mentioned, if an SIMD instruction is running for too long, the operating system will have to interrupt it mid-cycle, save away its registers, and then reload them. Well, if you wanted to do this in parallel over a very large set, like 1,000 vectors, that's going to run for milliseconds to good portions of a second. And you wouldn't want a single instruction running for that long unless you spin it off into a separate process thread so it can go over there and munge for a while. What you want to do is offload that from the processor, not make the processor stick on one instruction for an extremely long period of time. So let's think about using the Field Programmable Gate Array as a chip that you put on an add-on board and you plug it in via something like a USB interface. Yeah, you could load a quantumistic instruction set into the gate array. That would be optimized instructions with optimized data widths for just what you're trying to do. Load it in there, have it do its thing, get the data back, look at the data. Is it optimal yet? Nope. Have it run another iteration, kind of like optimization runs on a quantum computer, but they would be very much faster and without all the fragile qubits. But by doing it through something that's programmable, like the gate array, you can now make trade-offs. You can say, I want more stages, or I want different sets of logical operators, or I want wider values. You can balance that however your algorithm needs it. So you load the data in, you essentially crank the data from its input into the first stage, you run it. The circuit will run for probably less than 1 second. There's no disruption, there's no context switching. Whatever process is doing this owns the add-on board for the duration of it, likely less than a second. And then when it gets done, it says, do I want to try that again? Do I want to do another run? Or am I done? Have I got my optimal value? Is this the 50th run and it's good? We're good at this point. And then I can release the add-on processor for use by other applications. But if it's connected via USB, I can have multiple of these things connected. And I can either have multiple applications all doing their own quantumistic things, or I can have one application that needs even wider values, and they can broadside and do multiple of them at the same time in parallel. But how would I connect these things up? Well, if it's a small enough amount of data, a 5 gigabit per second USB 3.2 serial interface is probably fast enough to load the data, load the program. If there's enough memory on the board, you might load a couple of different programs and decide which ones you want to execute at which time. So you don't have to go through the transfer of the program out to the USB interface every time you want to run it. Stored libraries. You could have multiple of these on a single computer because they're relatively cheap. Like I said, under $40 is what I paid for mine. It has 20,000 gates. So I could easily put a few of those together. But once I get a lot of data, and it's very wide, like, maybe thousands to millions elements wide, now it starts to get not slow within the gate array, because that's still running at gigabit speed. It gets slow transferring the data in, transferring the program in. Execution is very fast, and then getting the data back out. So that gets to be slow. So instead of using USB, we could use what is known as PCIe interface. This is a very much multi-channel parallel interface. This is the kind of thing when you plug that expensive video card in, it's got multiple PCIe channels and they're running at gigabits per second per channel. If you need it to load faster, not necessarily execute faster, but load faster and give you back the results faster, then maybe move from USB to PCIe. There are field programmable gate arrays that already are on plug-in cards that are PCIe based. Obviously, you have to have a computer that has plug-in slots on it. It's not going to work on a laptop. You don't have to go invent that wheel. That wheel already exists. And eventually, like all very useful components of a computer, they migrate from being something external to being something connected to being something plugged in to being something on a motherboard. And then they just throw it in the processor chip like GPUs and neural processing units. They just eventually all migrate that stuff into the chip that's the size of half a playing card. So superposition, if superposition is one bit that could be any value, non-deterministic, random, within a range, we can do that on a regular classical computer. We just put all the possible values in a row in our matrix, and then we make the parallel execution to calculate it. Whenever a quantum computer takes a 0 or a 1 bit in, makes it into a qubit, it starts out with a definitive value for a 0 and a 1, and then the qubit is allowed to be non-deterministic. So while it's running through all the quantum gates, it's running randomly whatever values it attains at that time. In the case of superposition implemented on a gate array on a classical computer, it would have all those values in a single row, and you would per stage each row. So it's an optimal approach. It's not precise, but you could literally, for as many gates as you have in your gate array, come up with as many values as you want. There's no non-determinism of it ever. It's all known values, but executes all known values in parallel. If you ever take a moment to look at a field programmable gate array these days, there's a whole lot of kitchen sink in those things. It's more than just an array of programmable gates. They put input-output ports on them. They put different kinds of memory. They might put processors for supporting radio communications, might be digital signal processors, phase lock loops. If you're doing video processing, you may actually have GPU components buried into the chip that is also your gate array. And that's so that they can do all these different things with programmable logic like gate array. There are actually software programming standards for how you convey the program, design and convey the program to a gate array. And this is referred to as very high definition language, or VHDL. So I can write a VHDL program that I can map to different gate arrays based upon their size and their speed and other features. And the program that I write is backward compatible. So I can move to a gate array that has more gates on it and expand things without, going back and reinventing the wheel. In the case of a quantum computer, if I want to move from a limited number of qubits quantum computer to a very large quantum computer, I may have to rewrite my quantum circuit algorithm from scratch, go back to the math and remap it onto the newer model computer. If I wanted to, I could probably run multiple quantum algorithm applications on this add-on processor and switch between them, but then that gets to be slow, so it's better just to have multiple add-on boards and deal with it that way. Or, as like I said, avoid oversharing. So if I have one of these add-on boards, would I want to share it with other applications at the same time? Kind of like doing a context switching thing. And the answer would be no, because it would slow it down. There have been, in the history of computing, commercial computing, there have been attempts at having a software-defined instruction set for the computer itself, where you didn't have a predefined, fixed set of instructions. Every time you context switch from one application to another, you could literally redefine the instruction set. Burroughs, their B1700 series computers, long obsolete, was a good example of this. They thought that because they could rewrite the instruction set as you change from one software application to another, you could write, let's say, a program in COBOL or Fortran or BASIC or whatever, and then the instructions that it uses would be very optimal for that particular programming language. So I could be running a COBOL program, a Fortran program, and a BASIC program, and when I switched between them on a context switch, I would reload the instruction set of the computer to be more optimal for that programming language. The problem was there was not enough storage to write the instruction set for multiple of these languages, and the context switching overhead would be its Achilles heel. It couldn't switch fast enough. So if they wanted to do that today, it would be much faster. They could leave multiple instruction sets loaded, and on a context switch, you just change the instruction set. But what they found out was, instead of spending all the effort to make different instruction sets and then writing different compilers for different instruction sets, why don't we just make the CPUs faster, optimize the compilers, actually have fewer instructions as things move from the complex instruction set to the reduced instruction set, CISC to RISC, and maybe use all those available transistors to have multiple cores, hundreds of cores on a single CPU chip. If we break apart the instructions down to their minimum set, we could actually get a little interpretive engine going inside the CPU. It would be executing these incredibly tiny pieces of instructions at a very fast rate, at a femtosecond rate, not nanoseconds or picoseconds, but femtoseconds, so 1,000th of a thousandth faster. And that's how most of the big CPU chips are actually implemented, is they actually have a very tiny, ultra-fast switching processor that actually implements the instruction set. So as I was mentioning about gate arrays having their own programming language that's portable across different types of gate arrays, there are libraries, and commercial vendors pay for these libraries. So if I said, I want to make a gate array that does some special function, but I need kind of a little core of computer chip added in there, I can actually take a library for an arithmetic logic unit. It'll do, add, subtract, multiply, divide, some Boolean logic, some conditionals. I can actually get a software library in VHDL that says, here's an ALU, here's the characteristics of it, and plop that into my FPGA, and then connect up lines to that data. And now I have a processor specifically designed for my needs. You can decompose those ALUs into their individual instructions. If you say, I want to make a digital signal processor, but I don't need all those floating point things. I just need the integer, or I just need positive integers, or I don't need 128-bit and 256-bit. I just need 8-bit and 16-bit. So you can decompose those libraries to make the instruction set occupy fewer gates and run faster. And digital signal processors do this all the time. GPUs do this all the time. They have reduced instruction sets for specifically what they're trying to do, but don't need all the other stuff. And that frees up more gates to do other things. And then when they get it all just right, they can burn that FPGA into an actual circuit design, because the same thing that gets you the soft load of the gate array can get you a hard circuit design off of pretty much the same VHDL circuit design. So if I said, okay, I want to create one of these quantumistic FPGAs, how do I select the chip that I want, the FPGA chip that I want? You're going to be loading data in, it's going to grind away on it, and then you're going to get the data back. There's no video interfaces, there's no audio, there's no radio frequency stuff. It doesn't need to be a high-speed bus, no PCIe, no LAN, just good old high-speed USB is fine. So find the right chip for it. You want one that has the most gates on the chip, but you don't want all those fancy functions. So if you choose the subset of that You're going to have more gates to work with. It's going to reduce the chip, and that's how you choose the chip. I'm not going to give you any manufacturers or model numbers. Now I've got the chip. I need a board that I can plug into the computer. And yeah, there are USB connected ones. And if you select one that's connected by a USB 3.2, that's a fast interface. It's 5 gigabits per second. Get it with a USB style male connector, not like a USB or a micro USB or a USB-C. Just get USB-A because that can just be adapted with a plug. You don't need a lot of fancy displays or counters or anything that show up on the board. You maybe need a couple of status LEDs or maybe just one LED that does multiple colors. Is it loading? Did I put data in it? Is it running? Is the data ready? Basic status stuff. Maybe if you had enough RAM that you could load your Quantumistic program in there ahead of time to define the instruction set, it would be faster to load. How much RAM would you actually need on the board? About 100 times the number of gates. So a 20,000 gate array, maybe about 2 megabytes worth of storage to hold the program for loading. Now, if the data that is a result of your program running is large, you might want some RAM for that. But now what if I wanted to share that board with multiple applications? I might want flash storage on there so that I could store multiple Quantumistic programs and then select which one I wanted to load now and run. But I don't need a lot of fancy interfaces, so avoid the fancy interfaces. So if I had, let's say, a particular application that needed a particular instruction, I would want to shrink that down so I got just that instruction across all the value widths per stage. So if I'm looking at a quantum computer, I need one of these Toffoli gates, and the Toffoli gate actually is multiple gates occupying space. So if I implemented what I needed at a particular stage as a Toffoli, it's going to waste gates because I don't always need all the fancy capabilities. So if I can say I want a specific instruction at a row column of my algorithm, that consumes fewer gates. So if I can reduce the instruction set of my arithmetic and logic unit down to just the instructions I need, that would free up more gates for making wider or more. And the instructions only need to be as wide as needed. I mentioned that you could decompose an arithmetic logic unit or ALU library for whatever bit widths you need, 8, 16, 32, 64, or 128. If you're only going to be doing 16 or 8-bit, you don't need to be processing all the other bits. That saves you gates. If you want to do 19 bits worth of data and you're using an off-the-shelf ALU, 19 is greater than 16, so you're stuck processing and storing gates for a 32-bit instruction. A lot of waste of gates. So if you said, I want a 19-bit data item, and it's going to be like an add, then I have two 18-bit inputs making one 19-bit output. If you can decompose the instructions down to only what you need, it frees up more gates. A general purpose classical computer's ALU has a lot of things called registers or scratch pad registers or general purpose registers. Whenever you run an instruction, there'll be bits in the instruction that says, I want register X or register Y. And that's as part of the instruction. If you're writing your instructions into the gate array specifically for your purpose, then you don't need a lot of bits to decode for it to say, well, which of the many registers should I want? You can hardwire it directly saying, this instruction only takes a value from register X and works with the value from register Y, and then puts it in memory or puts it in register Z or back into X or Y. So you can save the instruction processing time and the number of bits it takes up. And if you can not have to load data from registers, then that saves you processing time. When you run an instruction, let's say I want to do an add. If I'm going to do an add and it's going to burn up one of my registers, like register X, so I take register X, add register Y, and it puts the value back in register X. I have to, at one point during the processing of that add, have an internal register that I'm like overlaying the value in. By hardwiring all these things together specifically for my purpose, I don't have to do that anymore. And that saves gates. So as mentioned in the last presentation, the performance per instruction processing performance of a classical computer is on the order of 2.5 billion instructions per second versus a quantum computer running at about 25,000 operations per second. So if I can flip my quantum algorithm over to a classical computer, I can be executing many millions of instruction stages per second in parallel without needing those full width instructions. If I can do the full width of what I need, of all the values, then in a single instruction, I can do a single run. And if I want to do multiple runs, I just put multiple stages in there and the values flow through. But even if I only do one run at a time, one stage at a time, I'm running so much faster, over 1,000 times faster on the classical computer than the quantum computer that I can afford the luxury of loading the data, doing a run, getting the data off, loading next iteration of data, doing the run, getting the data off. That would still be quite a bit faster than the quantum computer. And because it was running on a classical computer, I would have end-to-end traceability. If I wanted to gather individual decision points in the flow and say, I got down here at the end, how did I get there? What was the path that I went through? On a quantum computer, that traceability is just not something you should be looking for because it introduces more data and more fragility to errors. But on a classical computer, there's no problem. As long as we have RAM to store the data in, store the data. So let's start with something simple. I want to factor the primes of a number n. This is used in encryption and other things. But using my cheap 20,000 gate array, how many values could I get out of this thing? And it turns out it's 9 bits. So I can factor a number in the range 0 to 511 in a single execution cycle because I have all 509 values. I don't need 0. I don't need 511. I don't really need 1. And I can skip over 2. So right away, I'm filtering it down to just the things that are meaningful. But I can put those in one entire row within the gate array, and I can do my necessary divide in one step in parallel. But if I had more gates, if I spent more money on a bigger gate array, then I could either have another stage of them, or I could take that 9 bits and widen it out. And just because you have a larger number doesn't necessarily mean you have more prime factors. As you get to bigger and bigger numbers, the prime factors doesn't really grow, but the number of repeats of them are. So for example, the number 1 billion has prime factors only 2 and 5, but it repeats 2 9 times and it repeats 5 9 times. So just because you have a very large number does not necessarily mean you need to be able to process out a lot of different prime factors. 5 is quite a large number of prime factors. 4 is the lion's share of it. And if you just want a meaningful quantity of them, even 3 prime factors that repeat can get you a lot of processing. So if I said I wanted to do 0 to 511, how many primes are in that range? There's only 97 of them. So that's a pretty good saving right there. Instead of doing 0 through 511, I only pick the primes that exist within that range. Those are the only ones that could be factors. And therefore, instead of having 512 values wide, I only need 97 values wide. So there's a big saving in reducing the number of primes you actually need. Next thing is I need to divide on every one of those values, but I don't need the quotient. I don't care what the quotient is. I'm looking at the remainder, and I'm not looking at all the bits of the remainder. I only want to know if the remainder is actually 1 or not. Because remember, primes are number divisible by itself and 1. If something comes up even and it's a 1, I know I've got a prime factor. If something comes up and says, you've got a remainder that's going to have to do a shift because it's got more significant bits than just the value 1, kick that one out. I can early end that one. So it will come to the conclusion quick for the ones that are fractionally prime. And once I get this ripple of all these parallel divides and I get the values out, I can use those values to calculate a successive run to narrow things down. This is for when I have a prime factor and it repeats like, 4 or 5 times. So I do additional runs with the data until all my values come out as there are no more prime factors. Everything came out as 0 bits. But if I can have wider than 9 bits, I can have more values. Now I can actually do more parallel divides on a single step, which makes it calculate the runs faster. So if I decompose the actual divide instruction itself, a divide's nothing fancy. Back when I was in high school working on very primitive computers for the day, very advanced educational computer for the day, but very primitive by today's standards, I learned what a divide is. A divide is nothing more than a loop of subtract, compare, and shift. So you take a value, you take another value, you subtract from it, and you look at the result. And if it doesn't fit, then you need to shift over and get another value. But a subtract itself can be decomposed. A subtract is nothing more than taking one of the values, doing a 2's complement of it, and then adding it. So a subtractor is not really a subtractor. It's modify a value and do an add. A 2's complement is nothing more than a 1's complement, which is flip the bits, and then add 1 to it. So I don't need a subtractor. I don't need anything dedicated to do 2's complement. I just need something that will do a complement and an add. And that will give me all the lower level components. The next one is a shifter. So if the value comes out needing more, like I need to do a carry or a subtract, then a bit shifter. Each of these operations, each of these functions takes a certain number of gates for every one of the bits of the values that I want. So if I added it all up and said, I want a divide instruction, how many divide instructions can I get to execute in parallel for 9-bit wide data? Turns out that it's 144 gates per divide instruction, and the total number of gates turns out to be 13,968 just for my parallel divide row. And that fits in my 20,000 gate array. And I'll have some left over for doing miscellaneous wiring and such. Many of these prime factored values have less than 5 prime factors. Many of them repeat. So once I get one row, I can put the data in, execute a row in one cycle, very fast at one cycle, execute the cycle, take that data out, create another set of data in, flip it again, do another divide. If I can do this a small number of times, I've got my prime factors. Remember, it's only for prime factors 0 to 511. If I have more gates, I can make it wider. And I can continue to do this until all the decision bits come out as 0. There's no remainders. But that's the total number of iterations is capped. So for those of you that want to know how this fans out, how it gets wide very fast, the number of primes is actually a designated mathematical function, pi of x or pi of n. But it's not related to 3.14159 whatever pi. It's just they gave it that symbol. Why they couldn't pick a different symbol, they've got an entire Greek alphabet, but the pi of a value is the number of prime numbers between 1 and that number. There is a natural logarithm formula for calculating these that's quick. The problem is it's approximate. When you start out at a certain level, as it gets a bigger and bigger and bigger and bigger number, it gets off by more. So it's asymptotic approximation. But I prefer to have the actual count, so I calculated out the numbers of primes. And you can see that if I want, let's say, a 24-bit number, the maximum value is 16,777,215, of which 1,077,777 of those are primes. If I have 24 bits, I need over a million plus individual values. So that would be one clock cycle but I need a lot of gates to implement that. And as the number of bits goes up, it gets to be incredibly large numbers. I didn't even bother putting the commas in for 128 bits. And obviously I did a copy and paste for the 256 and the 512 to get all of the commas in the right places. But the 128, 256, 512, and 64 are they're just not doable without a lot of hardware. But nowadays for AI, mainframe computers, supercomputers and such, we tend to spend a lot of money to do a lot of things in parallel. This is an algorithm that can definitely run in parallel. So the largest gate array I could find, largest single gate array I could find has 9 million gates in it. And I can do an 18-bit prime factor solution with one of those gate arrays. And I can do it in under 100 clock cycles. 100 clock cycles, even at the megahertz level, is I can solve prime factors 18 bits wide all day long, and you'd never even see it delay. But if I wanted to do that for a very much larger number, let's say a 32-bit number, I would need 25,364 of these 9 million gate arrays. But I don't need it all in one chip. I can have lots of them. I can have, a board full of them. I can have multiple of them on the same computer. I can have multiple computers that are networked together, kind of like they do with supercomputers, kind of like they do with AI computers. If the same concept of expansion is applied to this, then having 25,000 gate arrays in a computer that has 4 million CPUs, 4 million cores, not a problem. So what they're doing with the AI supercomputers, just the expansion concepts, apply it to this. So the actual prime factoring program would be single input, row of divisor values, parallel divide instructions. There would be constraints on what we need to worry about to reduce the number of gates. And you have a row of dividers that all you need is 1 bit out from each one of them that says, is the result actually 1 or a number other than 1, a fraction? Now, if we did this using VHDL, then the brand and model of the gate array is really not something that the person writing the algorithm has to worry about. But if you remember from the last presentation, if you're writing something for a quantum computer, there's a whole lot of quirks you have to learn that are manufacturer specific, model specific, and as they age, even instance specific quirks that you have to adjust your algorithm for. But if you're using a gate array to do this, then all of that can be avoided, and you have one programming language model for doing this, regardless of who the manufacturer of the gate array is and how many gates are on the gate array. So in summary, should we really wait for quantum computer hardware to support bigger and more additional algorithms? Sure, go ahead and spend the billions. Do that if you really want to, but could you cut off like a little slice of a few million to just look at doing quantumistic computing using gate arrays? Off-shelf gate arrays, just demonstrate that it's something that's meaningful for certain applications. Maybe assign a few gate array knowledgeable hardware and software engineers to evaluate at least the potential using a small gate array. If it turns out to be meaningful, and at least for the smaller numbers of essentially wide qubits, it kind of knocks the legs out from underneath the quantum hardware manufacturers, I say so be it. It's more about motivation for them to do better. More qubits, faster, cheaper, more reliable. Maybe doesn't need close to 0 Kelvin to run. By removing the low end from their business model and giving that back to the enhanced classical computers, that may be an incentive for them to, if they're serious about it, progress it. If they don't have the money to seriously progress it, then maybe move over to the quantumistic world. So I think that ultimately you're going to find that quantum CPUs, maybe quantumistic ones, are going to be added to classical computers, much like GPU cards and NPU cards and DSP cards were add-ons. The quantum or quantumistic add-on will start, and then they'll eventually realize we can put this on the motherboard, or we can put this in the same processing chip. Or I remember back that Early computers didn't have integer multiply and divide instructions, didn't have floating point instructions, didn't have trigonometry tables. Nowadays, all the trig values are just hard-coded into tables. GPUs, the CUDA cores of GPUs are now merged into the CPU chip, and natural language processing NPUs are either on the motherboard or in the CPU chip. Computing history optimizes things, so just be prepared to repeat itself again. Some of these links are from last time. Some of these links are new for this time. Like the Burroughs B1700, if you're curious about that beast. All about primes. And then if you really want to get into the instructions, the actual instruction logic of a computer, what is a division instruction? What is a subtract instruction? How do you do a non-circular shift instruction? And then the financial folks thinking that quantum computers are just a pump and dump, or you're going to find a lot of failing SPAC go public mergers. Comments? Questions? Did you learn something new this time that you didn't learn last time?
Too many numbers.
Yep. Well, luckily, I sent you the PDF and the email, so you don't have to look at all the numbers at once. You can look at things that interest you.
Thank goodness.
Yeah. I know there are a lot of, the numbers grow rapidly. That's thought of as the Achilles heel of classical computers is iteration. The number of loops, the number of loop executions you have to do is just so large that you'll never be able to do it in the number of seconds since the dawn of the universe.
No,
Well,
that's
not
for
if you're
sure.
doing it one divide instruction at a time, but what if you're doing like 40,000 divide instructions in parallel? That's going to eat away at a little bit of it. And what if you're executing them at gigabit speed, gigacycles per second speed instead of kilocycles per second speed? That's going to improve things.
Well, it improves it, but you're still on an order of n, not an order of n squared.
That is incorrect. That is incorrect. I'm parallel processing them m at a time. The total, you're correct, is NP complete. But NP complete does not mean you have to execute n one at a time. So the more gates you have, the broader you can make it, and you preload all the values, and then you just run the divisors. So you can click through many thousands of them in one CPU instruction cycle time.
But many thousands is still n, not n squared.
That is true. But if a quantum computer is only executing 20,000 instructions per second, and the classical computer can execute 2.5 billion instructions per second, even if you can't do them all at once, you can do many more of them in the same amount of time. And remember, a quantum computer is not optimal. A quantum computer does not derive the final solution. What it does is it relies upon the non-deterministic randomized values that you run through again and again and again and again until you get a value that's a close approximation of optimal. Whereas with a classical computer, you run it until it is optimal.
Okay, I'll think about that.
Yeah, just think of it this way. If I have a non-deterministic value for a qubit until I measure it, but when it's non-deterministic is when it's going through all my operators, all my functions. That means that the input to a function is non-deterministic and could be repeatable. I may not fully execute the entire population of possible values. It's the part they don't tell you. It took a lot of video watching before I went, hey, wait a minute. When they talk about optimizations, you may never get a fully optimal solution. you may get a close enough solution, and that's, what they don't tell you.
Mm.
You'll never know how much you didn't know until you know what you didn't know. Okay, I will come up with a non-quantum computer related topic for next week. I will try and find something that's more not so deep into the minutia and more focused on things astronomical.
Mm.
Okay, any comments or questions before I stop recording?
Nope.
Hearing nothing.